Okay. So I don't know, people are not joining, but yeah, I'll start. So the timing was 4. Yeah.
Okay, sir. Okay. Okay.
Yeah, there are some people waiting in the lobby. Hmm. Okay, then so I'm Robin. I'm from Indian Institute of Science. So today I'll be solving your doubts regarding assignment 2. So assignment 2 that you have to submit by 8th, right? So I'll do some previous year problems, which from which you can get idea to solve the current assignments which are in this year. So right, we'll start with few of the questions. Okay. So you can see my screen, right? With problem solving session on the page, right? Okay, fine. Hmm. Oh my God. Yeah. Uh, can someone say whether you can see my screen, right, properly? The one, the where I'm pointing this ground state.
Yes, sir. Screen is clearly visible. No problem, sir.
Okay.
Yes,
Okay,
sir.
fine. Let me admit all the guests. Yeah. Okay. So the first problem is you have to find the ground state energy of the. It is being recorded, right? Yeah. Okay. So you. Oh my God. So yeah, you have to find the state energy of an electron enclosed in a box of size this A. So you're assuming this as a infinite potential. So the problem would be sort of this, where this is X and this is Y. So your potential is infinite between from 0 to minus infinity and from 0 A to infinity. But between 0 and A, it is 0. So for that, if you solve the Schrodinger equation, what do you get as the eigenstates? You just get um, h bar square n square pi square by 2m a square, right? So now you have to use h bar c and mc square. So what you would do, you would multiply hc square on the top and pi square. So you'll also divide by c square. So then you'll get n square pi square by 2m h bar c whole square by mc square, right? So now you can just use the values directly, whatever is given. So you know h bar c is given as 200 mega electron volts femtometer, right? So what would be that? Which is 4 into, and there is also zero point 0.5. So okay, so this would be, yeah, so 200 square, because you have to find it for the ground state energy. Okay, so that would be, wait, so it would be 1 square into 200 square mega electron volt femtometer square pi square, which is 3.14 square by 2 0.5 mega electron volts, and A square. What is A? A is 10 power minus 20 meter square, right? Are there any guests waiting? I don't think so. Yeah. Okay, fine. Yeah. So after solving this and so converting the femtometer to meter, can you please switch on the your audio?
Sir, you are, I think, muted, sir. You are muted.
Can you hear me now? Can you hear me?
Yes, sir. Yes, sir.
Okay, perfect. You can ask the doubts if you have any regarding this problem. So 4 pi square, which is around 39 to 40. So whatever the exact number is, you can get. So it's 39.4 eV. So this is how you calculate the ground state energy for the electron, which is in the infinite potential problem, right? So now the second problem is for one-dimensional simple
Excuse me,
harmonic
sir.
oscillator. Yeah,
Excuse
yeah,
me,
yeah,
sir.
yeah,
Sir, for
yeah.
ground state energy, it means we have to put n equal to 1.
N equal to 1.
Okay, okay, sir. And if they will ask about the first excited state, then we have to put
Huh.
n equal to 2.
Then you have to put n equal to 2. So do you
Okay.
remember the wave function for the infinite potential? Well, it is this, right? Sine n pi x by 8, right? So
Yes,
where
sir. Yes,
n
sir. Yes,
goes
sir.
from 1, 2, 3. So 1 is the ground state. So n is not equal to 0. That means there is
Okay,
nothing.
okay.
So
Okay, okay. Fine, fine, sir.
size 0 means there is 0 probability.
Okay, okay, okay. Fine, sir.
Okay,
Thank you, sir.
fine. Okay, so this was the first problem. Now, similar to if you change the potential, you have a different problem, which is one-dimensional simple harmonic oscillator, in which the energies are evenly spaced and difference between two consecutive energy eigenvalues h bar omega by 2. So we have to tell whether this statement is true or false. So if you remember the simple harmonic oscillator energy eigenvalues, what are the eigenvalues? Which are n plus half h bar omega. Omega is the characteristic frequency of the potential, which is half m omega square x square. So where n can go from 0, 1, 2, 3. Okay. Yes. So now they are evenly spaced. You can check by taking en plus 1 minus en, which would be n plus 1 plus half minus n minus half h bar omega, which is h bar omega. So this would be the spacing between that, but in the question it is given that it is h bar omega by 2, so that statement is false. They are evenly spaced indeed, but the difference is the spacing is h bar omega, not h bar omega by 2. So these sort of problems will be in your assignment too, I suppose, in the which you're going to submit. Right. So now let's move to the third problem. Okay. So third problem says a particle of mass m is moving freely between x equal to 0 and x equal to a inside one-dimensional infinite square potential well. So it's the same potential which was in the first problem. Now you have to calculate the expectation value of position, which is x operator. So you have to calculate the expectation value of x, which you can represent by this. That will be a by b. So where b would be what? We have to find what is b. Great. So you know the wave function. Psi n x is root 2 by a sine n pi x by a. Right? So what is the expectation value? What is the for any operator in general? Let's say O operator. What is the expectation value of O operator? Do you know, Himanshu?
Sir, I think I
So
am forgetting.
it's like, okay, whatever operator is, so it's like, what is the probability? Psi star psi. So basically you have to find the probability, it is at what x. So that would be O psi star x psi, which is dx, between minus infinity to infinity. Okay, there is a guest. Let's admit them. Fine. Okay, so what is operator O, which is x? You have root 2 by a sine n pi x by a. Again root 2, because this is a real wave function. There is no complex part in this psi. So then you don't care what is psi star and what is psi. Both are same for this problem. But in general, you have to take care if there is a conjugate and if psi is complex, then you have to take care of this thing. You can't just write both as same. Okay. So integral from 0 to a, because before 0 it is 0, the psi, and after a it is 0. So our integral will reduce from 0 to a. So you get 2 by a outside, 0 to a sine square n pi x pi square. Great. Let me add a page after this problem. Okay. So yeah. Right. So 2 by a, we have to do it for what? Ground state. The expectation value is what?
Sir, in the question, the function is not given. Na?
Yeah, function is not given, but we know in the problem they have mentioned it's one dimensional infinite square well potential. So you should know the square well potential. You can solve it using the Schrodinger equation, and that would be the wave function, right?
Okay.
Yeah. So now you have to do this integral, which is 1 minus sine square x is 1 minus cos 2x by 2, right? So this is the simple trigonometric formula you have to use. Cos 2n pi x by 2 by 2 dx. Now, either you can choose to solve this whole thing, but there is a simple trick. What is that trick? Is, since x is hmm, okay, so x square by 4 it would be from 0 to a minus x and cos 2n pi x by a. You have to do this integral. Fine. That would turn out to be 0 actually, but we can still do it. Okay. Why the guests have to wait? Why can't they just come? Okay, let's see. Admit all. Fine. Hmm. So 0 to a cos 2n pi x by a dx. Fine. The first integral would be 2a into a square by 4. Right? Now we have to do the second one. What would be the second one? Do you remember the product rule of integration? If you have sort of f g dx, if you do it like that way, you'll get this term as 0. So you'll be just left with a by 2, which is the expectation value of position operator. Now, if you think it intuitively, why is it a by 2? Why did we just do this integration? We could have just said it in a simple way. How? Let's see how. Edge page after. Yeah, fine. Okay. So if you plot the wave function, let's say you plot just the ground state wave function. That would be what? This thing, right? It is 0, it is a, it is a sine pi x by a, which is 0 at x equal to 0 and at x equal to a also. This is 0, but in the middle it is the maximum value. So what is expectation? If you take a measurement again and again and if you average out, where is it gonna be most probable? Most probably, where would it go? The particle is gonna be. So if you can see this psi x, you can easily see it would. If you make the measurement many number again and again for a large number of times, you'll find the probability that the particle would be at a by 2 in the middle. So you could have just answered without also calculating this integration. So that's the simple way. Okay, but this might not be very intuitive for every potential. So do you guys understand that? Any doubt in this third problem? You guys can hear me, right? Okay, fine. I hope I am audible. Yeah, fine. So, right. So there is a fourth problem now. For an infinite square well potential, if the width of well decreases, what happens to 0 point energy and momentum uncertainty? Okay, so let's say you have an infinite potential well of the width A, right? And they are saying if it decreases, what happens to the 0 point energy? Okay, so what would be the uncertainty in the position in this case? That would be typically around the A, which is the uncertainty in the position. Delta X would be around A. If it's changing, then using the uncertainty principle, what you can, let's say you are using the minimum uncertainty relation, which is h bar by 2, right? So you can get delta P as h bar by 2a. So if they're saying if width of the well decreases, that means a decreases. And if a decreases, this delta P would increase with decrease in a. So yeah, so delta P, the uncertainty in the momentum, would increase, right? So now, if you think intuitively, if the uncertainty in the momentum is increasing with decrease of the width of the well, then particle will move faster and faster, right? Then its 0 point energy should also increase, just intuitively. So this would also increase. So which is the most probable the correct option is B option. Both will increase, right? So these were the easy problems. Now let's go deeper into the math. So a particle of mass m is subjected to attractive delta function potential, which is Vx equal to minus V naught delta x. Okay, which is the what sort of potential is this? If you want to draw the graph of this, let's say this is y, this is x. Okay, so your potential is V naught, but it's a delta function. So and with a negative sign, so it would be the delta function at 0, like this, and 0 elsewhere. So this is the potential for the problem. Okay, fine. And let me add pages. This would be a bigger problem. Uh, okay. So yeah, let's start. Now you must have solved the infinite square well potential, right? So idea is to solve this problem in a similar way to find the ground state energy or the bound state energy in this case, because in this the particle would be bounded, right? So how do you start when you do such quantum mechanics problem? You first write the Schrodinger equation. Let's write that del d squared psi, so second derivative of the psi, plus 2m v naught by h square delta x, because that is our potential. So psi x minus, actually, okay, wait, this would be minus equal to E naught, E, which we have to find out, 2m by h squared psi. Right? So this would be your Schrödinger equation. So rearranging the signs, you would get this 2m v naught by h squared delta x psi x plus 2me by h bar square psi. Okay. Now, for x not equal to 0, what would happen? Your delta x would be 0. So let's write for these region. So let's say this region, and this region. What would be the thing? Okay. So for x non-zero, your Schrödinger equation would be d square psi by dx square. This term would go. This term would go. So 2me by h square psi equal to 0. Fine. What sort of solution this Schrödinger equation would have? If your E is because you have to find bound state, right? So your E must have to be negative. So in that case, your solution E is negative. So then your solution, your second order differential equation would be sort of this thing. So it would be dx square, let's say minus k square psi, where your k square would be 2m minus 2m e by h square. Right. Right. Yeah. So what would be your equation? So your solutions would be exponential solution, because now this thing would not give you the plane wave solution. It would have given you plane wave if there would have been plus over there. Okay. So your solutions would be e to the power, let's say a e to the power kx plus b e to the power minus kx, the linear combination for x non-zero. Okay. So far, so good. Okay. Now you have to use the condition that your wave function has to die down to 0 at the minus infinity and plus infinity. So if you're at the plus infinity, it can die down to 0 only because of this term. So this means your psi of x would be e to the power minus kx for x greater than 0. Okay. With some factor, let's say b around. Yeah, this b. Okay. But for x less than 0, at x tending to minus infinity, which part would tend to 0? Not the b e to the power minus kx. It would be that part. This part would go to 0. So for x less than 0, this would be your solution. So far we have gotten the sort of general solution for the problem. Okay. Let me admit the guest. Okay. Yeah. So now you have sort of general solution. But what is our goal? Our goal is to find the bound state energy. What else can we have to find this A and B for this psi? One thing is continuity of the psi. At psi should be continuous, right? So we can use that at x equal to 0, your psi of x at 0 negative and psi of x at 0 positive should be same. Okay. So that would mean your A has to be equal to B. Okay. So you have further reduced the solution to this thing. A times e power minus ikx, A times e power kx for x greater than 0, the negative one, for x less than 0, this one. Okay, now we have just one constraint left. We have to find A. Okay, Anuj, you have a question? Yeah, ask.
Sir, will this recording be shared in the group?
What?
Sir, will we get this recording after the
Yeah.
class?
It is. The session is getting recorded. You can
Okay.
see, right? It is getting recorded.
Yes. Okay.
Okay. Yeah. Okay.
Sir, in
So
announcement, it will uploaded, right?
not in announcement, it would be uploaded in the YouTube channel. So I'll share it with you, what the channel is, so you
Okay.
can go and see it. It would be
Hmm.
public one. Yeah.
Okay.
Okay. So now in this problem, what we have to find? You can see we have to just find A now. After we have A, we can also find E. What is the bound state energy? Now, what else can we do? So your function is sort of this, like this. It is e power minus kx. It is e power kx. So what if you have your Schrodinger equation, which is t square psi tx square plus 2m v naught delta x by h square psi plus 2m e by h square psi equal to 0. Now, if you, this is going to be a big problem. Let me add a page. 1 and 2. Cool. So if you integrate around this region, around 0, let's say this is the region, minus epsilon plus epsilon, where epsilon, what we will do, after we want something, we'll turn this epsilon tending to 0. Okay. So if you integrate this thing between minus epsilon and plus epsilon dx plus 2mv naught delta function h bar square psi dx from minus epsilon to plus epsilon and 2me psi dx epsilon to plus epsilon, right? So this should tend to 0. Okay, good. So last term is very simple. You can tape the EMB by h square, and this minus epsilon to plus epsilon psi dx would be 1. Why it would be 1? Because it's a delta function. If you take delta function, the integral from minus infinity to infinity for delta function is 1. But it is already 0 at epsilon. So there is nothing after epsilon, there is nothing before minus epsilon. So if I change these limits to minus epsilon, and let me erase it. So if I change these limits to minus epsilon to plus epsilon, it would still be 1. Okay. So right, this term, last term is something which we can say is easy one. Now the first term. What is the first term? It's a second derivative. So the integration of second derivative is what? It's the first derivative. With at what? At epsilon minus d psi by dx at minus epsilon. Now what about this term? Again, you can take 2mv naught h square. You have minus epsilon v naught. Sorry. Delta x psi dx. Fine. Now what about this term? This we claim this integration is 1. What about this integration? Again, you will use the property of the Dirac delta function, which is f of x into Dirac delta of x dx from minus infinity to infinity gives the value at the center of the Dirac delta, which is 0, f of 0. Right? You use these two property to solve this equation. So what do you get? You get psi at x equal to 0. Good. So what you are left with, x equal to plus epsilon minus del x equal to minus epsilon plus 2mv naught by h square, and that is psi at 0 and 2m e by h square. So this is what you get. Good. Now we also have psi at x equal to x greater than 0 and x at x less than 0. So for this term, we'll do the derivative of what? A e power minus this x. For this, what we will do? The derivative of a e to the power plus kx, and we put x equal to epsilon and x equal to minus epsilon, right? And at psi at x equal to 0, what is the value of psi? It is just a. Okay, cool. Hmm. Right. Yeah. Wait a second. The last term is what? It is this psi dx. Oh, sorry. So it is not delta dx. Integration of not the delta dx. It is the integration of psi dx. So that is 0. Let's say your wave function is this, right? If I'm taking close to 0 at minus 0 and plus 0, the value, and if you want to find the area between this, so area between these two lines, let's say these two lines, what is that? When epsilon tending to 0, it is 0. So the last term has to be 0. So I should have made it 0. This last term would go to 0 because it's not the integration of delta with x, it is the integration of the wave function with dx. So which would tend to 0 when epsilon would tend to 0. So you won't have this term. That's what I was saying. Why is something odd coming out here? Fine. Okay, good. So what do we get? The derivative of this is minus k a, and x at x equal to epsilon, which would tend to 0. So you would get e to the power minus 0 as 1, right? Minus k a plus 2m v naught by h square a. Now the a obviously has to be non-zero. So the only zero term would be what? Right? Okay. So here, this is now what is the equation you get? Since the wave function has to be non-zero, right? Your a has to be non-zero. Otherwise, there would be nothing. Okay. So this is non-zero. Then this term has to be 0. Okay. So what is that? Now what would this give is mv naught square by h square. Now we also remember what was k. K square was, okay, we know k square. So let's square it. M square v naught square by h bar 4. Also k square was minus 2m e by h bar square. Initially when we defined the k, it was this. Okay. So from that you can get E as minus h square m square v naught square by 2m h bar 4, which is minus m v naught square by 2h bar square. So this is your bound state energy for the Dirac delta potential. Fine. So what is this option? Minus m v naught square by, it's a C option. Okay. So this was the Dirac delta potential problem. Good. Now we move on to sixth problem. It is also double Dirac delta. Okay, now there is a double delta function, not just one. Is someone waiting in the lobby? No, no, fine. Yeah. So particle in one dimension. Okay. Sorry. Particle moving in one dimension is confined by double delta potential, which is minus g of delta x minus a minus g of delta x plus a. Before you solve any problem or related to this potential well or any potential, you should always draw the potential in a xy plane. Cool. So yeah, at x equal to a, at x equal to minus a. So the strength of the potential is minus g at both a and minus a. Fine. So this one is at x equal to 0, which is minus g. Fine. And this one is at x equal to minus a, which is like this. And in between this, it would be 0. Before that, it would be 0. And after that, it would be 0. So this is your potential, right? Hmm. Now what you have to find? You have to find the general forms of the bound state odd wave functions. Now, right. So why they are just saying odd wave functions? There can be even also, because it's a symmetric potential. You can say it's symmetric about 0. There would be odd also. There would be even also. So parity can be either +1 or -1. Fine. So we have to find the general form for the odd wave functions. Right. So odd wave function has to be like before at, so it should not be symmetric about x equal to 0. So it should be something like this. Like your wave function can be like this, something like this. So it's not the, it's the odd function, but this is the even function. So we have to find the odd wave function for this. Now again, we can just do this problem very intuitively. If you see at x greater than a, your potential has to be this. It has to be this, right? Sorry, it has to be this. Okay, the wave function. Like at x equal to, it would be a pi minus kappa x for x greater than a, because it has to go to 0 at x equal to infinity. Now, so at x equal greater than a, it has to be of this form. So you can see in the option A, B, and C, it's this form with the strength negative or positive as the coefficient. And x less than a, what it should be. Hmm. So it can only be odd if what happens at x equal to a and minus, there is something wrong in this problem. How can your function become discontinuous at a? Right. Huh. Right. So it can be like, okay, so the odd wave function would be like this. So before this, okay. Yeah, so there is some misprinting in this problem. Odd wave function would be like this. So in between, it goes like this, let's say. Right. So the even would be the one like this, and this in between something, which has to be symmetric. So the only option where you can see this is the case would be the option D with opposite sign. So it has to be, I think there is some problem with this. It has to be minus a. X less than minus a. D option. I think there is problem in the typo error there. So your for x less than minus a, it has to be this, which is minus a e to the power kx. This is a e to the power minus kx. Only then it would be the odd function. Right, so it would be D option, but with this modification of the x less than minus a. Right, it's a very simple problem. You have to just intuitively draw the wave function. Let's admit the guest. Okay. Fine. Why are there so many pages in between? Yeah. So let's move on to the seventh problem. Again, the simple harmonic oscillator problem. So you are given the initial wave function psi at t equal to 0 for any x, where a is the normalization constant and psi naught and psi 1 are the ground state and psi and excited state wave functions of the harmonic oscillator. Does anyone know what sort of functions are the wave functions of the harmonic oscillator? Like what sort of polynomials are those? You must have solved simple harmonic oscillator. Does anyone know?
Dirac delta function.
Hello?
So will it Dirac delta? I
No,
don't
no,
know.
no. Harmonic oscillators के जो solutions होते हैं, what are the
Sir,
solutions?
I think, sir, Legendre polynomials.
Not
Hermite,
Legendre.
Hermite.
Hermite.
Oh,
Yeah,
Hermite. Okay,
these
okay,
would be
okay.
Hermite polynomials. For hydrogen atom, it is Legendre, and yeah. So for the simple harmonic potential, you get the Hermite polynomials. Nice. So which you can get either by solving the Schrodinger equation, or you can use the ladder operator method, which you'll be soon be studying in this course. So right. So what that is irrelevant to the problem. So we have to find the time dependent wave function, which is as a function of time, what would be the wave function? Right. Let's start the problem. When you start, you should just write what the wave function is given. Okay. A 3 times the ground state and 4 times the. So let's normalize that first. Then we will find what is the time dependent wave function. So for normalization, what is the condition? The integral between minus infinity to infinity of this probability density would be 1. Okay, so this would be a star a, which is a mod square, minus infinity to infinity 3 psi naught star plus 4 psi 1 star 3 psi naught plus 4 psi 1 dx. Now you know the solutions of the simple harmonic oscillator are the orthogonal solution. That means psi naught and psi 1 are orthogonal to each other. Actually, all of them are orthogonal. For any different n, they are orthogonal. So that means you will be just left with, out of the 4 terms of this product, you will just left with 2 terms, which are the normality conditions, the orthonormality conditions, which is psi naught with psi naught is 1 and psi 1 star with psi 1, which is also 1. So you'll get 3 square psi naught star psi naught dx, 4 square psi 1 star psi 1 dx. The other terms are 0. So you get the a bar square 9 plus 20, 16 is 1. So your a would be e to the power, a square would be 1 by 25. So your a would be 1 by 5 with some phase factor, which we are just ignoring because it's a mod. So you can say it's some e per I5, which we don't worry about because it would be same. Then your psi mod square would be independent of this phase. Fine. So let's ignore this. So your a is 1 by 5. Now what? But what we are asked to find is after the what as the Hamiltonian evolve with time, what would be the how the wave function would be evolving. Okay, that's what we have to find. So how do you do that? So if you know in the operator form how the psi xt would be, it would be summation of n equal to whatever the eigenstates are to infinity e to the power minus e n t by h bar psi x 0. This is the condition. How does this actually come? You will get to know when you write the Dirac delta notation, where you operate by this time evolution operator for the zero state. At t equal to 0, whatever psi you have, if you evolve with it time, you get this thing. Okay, so now your psi naught has what? Your psi naught has just the ground and excited state. So in that case, your evolution would be sort of 1 by 5 times 3 times psi naught x e and e to the power minus I e naught t by h plus 4 psi 1 e to the power minus I e1 t by h. And for the harmonic oscillator, what are the energy eigenvalues? They are n plus half h bar omega. So your E naught would be h bar omega by 2. E1 would be 3 h bar omega by 2. So your final solution would be what? It would be 1 by 5, sorry, 3 by 5 psi naught e bar minus h bar omega by 2t. This would be the first term, the 4 by 5 psi 1 e to the power minus 3 I h bar omega by 2t. So this is the answer. What is the option? Sorry, there is something wrong. No. I guess it's fine. So your option is D, I guess, right? It's D option, yeah, which is matching with what we did. So I think you would also have in the assignment two similar problems, the harmonic oscillator, potential well, and all that. So I think if you are able to get this, you'll be able to do. Yeah.
Sir, what is the physical significance for the harmonic oscillator?
What is the physical?
Significance for the
So where do you use this? So okay. So when you have a system where there are different atoms, right? So when they vibrate, what sort of vibration is that? That is the harmonic oscillator. So when you want to solve such problems, so and you look at the vibrational modes, you will look into this harmonic oscillator potential.
okay.
Yeah, fine. A beam of particles of mass m are sent from left region on a potential barrier of the form this. Okay. For E less than V naught case, what is the probability density in X between X2 0 to A? Is it 0? Okay, they are asking either this is true or false. So it's a simple problem. We can just physically see what is the case. Okay, again we'll draw the potential. Hmm. This is V naught, here it is 0, 0. If the particle is coming, which is at the energy E less than V naught. V naught is this, so the particle which is coming has the energy E, which is less than V naught. That means it has to hit this potential. If it would have been E greater than V naught, it can easily go. It can just easily go. But when it is less than 0, classically what should happen? It can't just cross the barrier because then kinetic energy would be negative. Right? But quantum mechanically, if you solve this problem using Schrodinger equation and you find the probability current, you would see there is some current after the x equal to 0. You know probability current, right? Which is the quantity to measure what would be the so that comes in the continuity equation of the wave functions, right? So if you solve it using the Schrodinger equation and you find the probability current at x greater than 0, you will find it is a non-zero value with some factor. It would not be exactly 0, it would be some non-zero value. So that effect is called tunneling. So quantum mechanically, particle has this tendency to tunnel through the barrier, unlike the classical case, where it's a classical forbidden region and it can't cross the barrier classically, but quantum mechanically, there is some probability with which it can cross the barrier. So that effect is called tunneling. So the whatever the statement they have made, that the probability density in the region x greater than 0 is 0, which is wrong. It would be some non-zero value. You can just calculate it by solving the Schrodinger equation. I won't go into that. You can calculate that. Fine. So the statement is false. Now what the problem is, a particle of mass m and energy E greater than 0 approaches an abrupt potential drop. So it's a potential drop now. It's not a barrier. It's a well. Okay. So it would be like it's a step potential where it is dropping. If it was 0 there, at x greater than 0, it would be minus. So I think the problem is in the question. It should be minus v naught. They didn't mention it properly. So yeah, at x greater than 0, it is minus v naught. At x less than 0, it is 0. So what they ask is that probability that it will reflect back if E equal to v naught by 8. So they are saying if your v E, matlab it is greater, E is this. So it is not in the barrier, it is not there, it is above that at E equal to v naught by 2. What is the probability that it will reflect back? Classically, can anyone tell what is the probability? We have to do quantum mechanically. But classically, what would be the probability that it will reflect back at this E equal to v naught by 8? Does anyone know?
It should not reflect back classically.
Yeah, it should just cross it because there is nothing stopping it classically, right? So classically, there is no probability, the probability is 0 for it to reflect back. But quantum mechanically, there is some probability with which it reflects back. Now we'll calculate that number. So let's do that. For that, what would we have to do? We have to write the wave function at x less than 0 and at x greater than 0. Then we'll find the probability current with which it reflects back. That's it. So let's write the wave function. So since it is above the 0 level, so the solutions would be plane wave in this region and also in this region. So it would be a to the power e power I k x k1x plus b e to the power minus I k1x, which is the reflected part. This is the incident part. Okay. For x less than 0. For x greater than 0, it would be some c e to the power I k2x with a different momentum because there is a potential drop by factor of v naught. So it would be a different k2. What are the k1 and k2? K1 would be just 2me by h and k2 would be, because there the kinetic energy would be more because there is a potential drop. So it would be E plus V naught by H bar. So far, it's good. Okay. So right, these are the wave function. Now what do we have to find out to get the reflectivity, the reflection coefficient, R? Like by what probability does it reflect back? What is the reflection coefficient? If you do the probability density, you find the probability current, you'll find your R would be B square by A square. Because A is the incident part, B is the reflected part. You can do that calculation by using this formula of the current, which is J equal to I H bar by 2M psi d psi star by dx minus psi star, something like this. Yeah, it was, I don't know the minus plus sign, there could be problem. So yeah, this is the way you'll calculate J, and you would get B square by A square for the reflected part. Okay. So now we have to find B square by A square. How do you do that? You have wave function, you use the continuity of the psi, and you also use the continuity of the derivative of psi. Now I have a question. How the delta potential, was the derivative of psi continuous? If the potential would have been the delta Dirac delta potential, we did the problem. Do you remember? Was the derivative continuous or not at x equal to 0? Does anyone know?
It should not be continuous, sir.
Yeah, for the Dirac delta potential, it should not be continuous, and we proved it by doing the infinitesimal integration around the x equal to 0. But for this case, it has to be continuous, right? So you'll use two conditions at x equal to 0. This, the part which is at x less than 0, has to be same as x at 0, and the derivative at x less than 0, and this has to be. So we'll use these two things to find the b square by a square. So what would that be? It would be just a plus b is equal to c from first equation, because you just put x equal to 0. For second, you take the derivative, and then you find the condition, which is ik1 minus ik1 b is equal to ik2 c. There is no reflected part at x greater than 0, so it's just the transmitted part. Fine. So what do you have? You have two equations to solve. B is k2 by k1 as c. So now solving this, you can find b by a. Right, you can find b by a. How? Because c is equal to a plus b, and c is also equal to this, so you can just take this k1 by k2 a minus b. Fine. So that would be 1 plus k1 by k2 b a. So b by a is k1 by k2 minus 1 and k1 by k2 plus 1. Now what is that? It's k1 minus k2, k1 plus k2. So mod square of that would be just square of this. And you know what are the k1 and k2? So that would be nothing but square root of e minus square root of e plus v naught, square root of e plus then square of that. Okay, fine. Yeah, cool. I'll also share these slides so you can just have look at what I did. Yeah. So right, your E. So we want to see at if the particle of energy V naught by 2 is coming above the potential, then how by how much it would reflect back. So you put E equal to V naught by 8, which would give you, let's simplify it a bit, V naught by E, 1 plus V naught by E. So E is V naught by 8, so it would be 1 minus 9 square root, 1 plus 9 square root. That is 1 minus 3, 1 plus 3 square, which is 2 by 4, half square, which is 1 by 4. So basically 25%. So there is a 25% probability that particle can reflect back. So that's what, which is not expected classically. So your answer is 25%. Yeah, great. So similar problem you can be asked like how, what, okay, one person, yeah, ask the question, yeah.
So sometimes we see that that is the k equal to root over 2 me by h cross. Sometimes minus root over minus 2 me by h cross. Why that is a change?
Sometimes you see 2 me, or sometimes you see it with minus, right?
Minus, yes. In alpha and all this calculation.
So okay, let me explain you. Right. So right. Okay. Let's take this potential, and this is zero. If you are coming with this energy, you have to just write the Schrodinger equation. There is no k as of now. K you define. K is not there as of now. Okay. So for this region, what would be the Schrodinger equation? Minus d square psi by dx square plus 2m, sorry, the potential. What is the potential? Is 0 over there, right? V equal to 0 by h square psi, and you have 2m e by h square psi. Okay, for region 1. Then you get the equation as this thing. Now e is greater than 0, right? So you can define, if e is greater than 0, that means your k square, if you define this to be k square, you can just define it as this thing. But let's say if your e was minus negative, let's say you are transmitting the particle from below this, then you can't define your k square as 2me by h bar square, because then it would be the state inside the potential, it would be the bounded one. Your e is negative, right here. Then you have to define your k square as minus 2me, and in that case your differential equation would be minus k square psi, which would have exponential solution. And that makes sense also. If your particle is below this potential, then your solutions, the wave function has to be exponential. But if your particle is coming from above this potential, which is 0, then it has to be plane wave. And it can only be possible if your k square is 2me by h square for e greater than 0. And for e negative, your k square is this, and that would give you this differential equation, which is exponential solution. For e greater than 0, you get this differential equation with plane wave solution. So it's matter of defining physically what should be your solution. Like either it has to be exponential or it has to be plane wave. So these are the typical cases. The way you asked, it can be either minus 2me by h square or it can be 2me by h square. So for what sort of cases? If your energy is above the potential barrier, then it has to be plus 2me by h square. But if it is below that, it has to be minus 2me by h square, the k square, because your e is negative in that case. It's a bounded one. Do you understand?
Yes, sir. Yes, sir.
Okay.
Thank you.
Okay. Fine. That is actually a basic question, and one should actually understand that. Otherwise, you can make mistakes. Yeah. So the last question is, consider a potential step of the form this 0 V naught, right? A beam of particles with energy E approach this step from left. So it's the same potential which I explained, Abhi, is this one. Step potential. Now what are they asking? If the particle, the beam of particle with this energy E approaches the potential step from left, the statement which best describe the reflection coefficient. Okay, that's a good question. So it's the same, similar to what I explained. Either your E can be less than V naught or E can be greater than V naught. So either your E can be this or your E can be this. E greater than V naught, E less than V naught. Fine. So we have to see for E greater than V naught what is the case. And for E less than V naught, what is the case for the reflection coefficient. Mm, okay, there are guesses. Okay, fine. Yeah. So for E less than V naught, we have sort of explained, right? There is a right potential step. Okay. Hmm. So actually, there is a problem with this question. They are saying that reflection is 0 when E less than V naught. E less than V naught, the reflectivity should be 0. It should be actually the something should reflect. Oh, sorry, what I'm saying. Yeah, something should reflect if E greater than V naught. Hmm. Reflectivity. Yeah, right. For E greater than V naught, classically what should happen for this case? Can you tell me? Anyone? We have already discussed this, I guess. For this case, when E greater than V naught, classically, what should be the reflection coefficient? It should be 0 because everything should just go, cross the barrier. Nothing should reflect. But in quantum mechanically, we have seen that R turns out to be non-zero for E greater than V naught. So A and D option says that. Fine. For E greater than V naught, it makes sense. For E less than V naught, they are saying either your R can be 1 or R can be 0. For this case, they are saying it should fully reflect. Now, total reflection and R0. R0 is definitely wrong. Actually, there is a mistake. The reflection is not total reflection because there is something transmitting. So how can it be full reflection? Because your condition is R plus T equal to 1. Right. So if at E less than V naught, there is slight transmission, let's say it is 0.01 or even less than that, your R has to be 0.99, which is close to 1. So what are they saying? That reflection should be complete, but there is something which should tunnel. So the only A option makes sense because R equal to 0 for E less than V naught doesn't make sense. There is nothing reflected. Obviously, even in quantum mechanical case, it should reflect back things, almost everything, but there is something which would tunnel. So option A is the best option out of this. Like your R is non-zero when your E is greater than V naught. So quantum mechanically, something should reflect. The R has to be non-zero. But when E is less than V naught, almost everything would reflect back, only something would tunnel. So that is approximately R equal to 1. So that's why I think A option is the best one, right? Okay, so we have actually time. So you guys have submitted assignment 1. Can you guys hear me? You have submitted assignment 1, right? Hello?
Yes, sir, we have submitted.
Yeah, okay. So that's why I discussed assignment 2 today because you have a deadline at 8. So there would be similar. I mean, you must have seen the assignment. There are similar questions, right? So you can solve the assignment 2 by the idea of this thing. But I'll discuss some assignment 1 questions also because I have to discuss for 2 hours, or maybe you can also ask me doubts because I have explained you the problems which you are supposed to do. You can ask me something else or anything related to your course.
If you kindly solve some of the questions from assignment 1, so we can check.
Okay, fine.
Like,
So I don't have the new one. I have access to the previous year assignments. So some of them would be similar, I guess, but I'll solve those. So these are the previous year assignment one, similar to what you must have done. So yeah, we can solve these.
Chat
Yeah.
box, I have sent one question. Could you please see that?
Can you say it again? I can't hear you properly.
I'm saying in chat box, I have sent one question.
Okay,
Once is
fine. Let's see that. Hmm. Right. So let's solve this question. Find the value of A. Okay,
it is easy, but
let's do this. Yeah. I'll do it at the end, maybe. Psi x is 0. Okay, I have to. I have an idea. Let's do something. I'll take this screenshot and just copy it there. Huh. So, right. So this is your problem. Okay, let's do this. A root 30. Very weird function, but let's do this. Okay. So you have to find the value of A. Then you can use the normalization condition, right? So, which is the integral from minus infinity of this is 1. Now at x less than 0 it is 0, fine. At x greater than L also it is 0. So the integral will remain just between 0 to L. And the wave function corresponding to that is this. So which would give you A mod square root 30 square x square L minus x square dx is 1. Okay, so you get 30 out, a1 square out, x square L square x square minus 2lx dx is 1. So 30 a mod square, which is lx cubed by 3 x L square x square, okay, x5 by 5 minus 2l x4 by 4 from 0 to L. Upper and lower limit, right? 3a mod square L 5 by 3 L 5 by 5 L 5 by 2. Okay, 30a mod square, take L5 out, it's just the 30, 10, 6, 15, 30 say 30 cancel, and you get just the a square L5 1 equal to 0, not equal to 1, sorry. Yeah, so you get A as L minus 5 by 2. I think that's what the correct option is. Okay.
yeah, thank you, sir.
Any other question? If you have, you send it the screenshot to the chat box. I can try solving. Do you guys have any other question? Please put it in the chat box. Or you can ask something intuitive, whatever you have listened in the lecture. So I can try also discussing that. Or then let's solve some problems which I have, sample problems for you. Okay, let's do some interesting ones. Let me open my notes. Mm, Fine. Okay. So let's do this. If you have a particle of mass in infinite potential square well with walls at x equal to minus a by 2 and a by 2, what would be the wave function? Now it's a very interesting problem. It's very simple, but it's very interesting. How? Let's see. So you know this problem in the way that if your potential is between 0 and a, right? Infinite potential. This is infinite, this is infinite. But what sort of potential they are considering is similar. Let's extend this. The only thing is it is shifted by a by 2. This is a by 2. So this is their potential. Physically, it's same. It's just that it is shifted in x. Otherwise, everything would be same. The wave function, the ground, the energy eigenvalues, they should be same physically, but mathematically they would change. We have to find how. So you know the wave functions for this, right? The psi nx is root 2 by a sine n pi x by a. Now they want us to find the eigenfunctions for this problem. If it's a shifted square well, then what would be the eigenfunctions? So the way I'll do it, you can use this way to find the eigenfunctions for any shift. Here it's the shift by a by 2. But in general, the shift can be by a by 3, a by 6, a by 5, or any other factor. You don't have to solve the Schrodinger equation again and again to get the wave function, but you can just use this shift criteria. So it's simple. How it's simple, right? So yeah, right. So you know the wave function between 0 and a. For the shift, what you have to do, you have to just make the change of variables for x to x plus a by 2, or sorry, minus a by 2, right? Because what is happening when your x was between 0 and a, but you want your x to go to uh, minus a by 2 to a by 2. How can it happen? If you subtract a by 2 from this and you get this. So this should be your new x, right? So then your x is nothing but x star plus a by 2. Okay. So now you have to just replace x by x prime plus a by 2. Hmm. Yeah. That page after. Fine. Yeah. So your wave function, new wave function in x prime, which is when your potential well is between minus a by 2 to a by 2, would be root 2 by a sine n pi x prime plus a by 2 by a. Root 2 by a sine n pi x bar by a plus n pi by 2. Now this is nothing but it would be just cos n pi x prime by a, because you know sine n pi by 2 plus anything is what? It would be no, it would be cos for n equal to 1, 3, 5, right? For n equal to 2, 4, 6, it would be sine again, right? So what they want us to find for n equal to 1. So for n equal to 1, it would just go to sine, sorry, cos n pi by, sorry, there was, n pi by 2 here also. A, yeah. So it would just be cos n pi by x by a for n equal to any odd, which is 3. And we want it for n equal to 1, so your wave function would be this. So many people would make mistakes. They would write the same wave function, which is root 2 by a sine n pi x by a. But when you shift your potential, your wave function would change accordingly with the shift of the variable, right? So you can get similar problems. You have to find it for the n equal to 2. N equal to 2, it would remain sine only. Okay. Okay, there is someone in the guest. Let's see that. Okay. Right. Please ask me any doubt in the chat box. If the new joinees, you can post your problem. I can try solving it. I have solved the question of the previous year assignment. So I would like to solve any random problem which you have. So this is one of the question. I have plenty more. Yeah, this is similar, right? This is, you have to just do the integration. But if you want me to do, I can do. Okay, let's do this. Chat box. Okay. Consider one-dimension potential of well with this using the uncertainty principle. Can anyone tell me what sort of uncertainty principle is this? Why it is not h bar? It's just h bar by 2. Why is it h bar by 2? Where does that come from? Does anyone know?
This is Heisenberg's.
Yeah, this is Heisenberg's, but why h bar by 2? Because in some books you must have seen h bar also. X delta p greater than h bar or h. But h bar by 2 is a minimum uncertainty. So it's something which you can actually derive also. H bar by 2 factor. So any other uncertainty principle is also valid. You can remove 2. It would also be uncertainty principle. But this is the Heisenberg minimum uncertainty principle. So I just wanted to point this out. Yeah. So you have to use this minimum uncertainty principle to get the estimate of the minimum depth of the well such that it has at least one bound state for an electron. Hmm. So it's a width 3 nanometer. What should be the depth of the well so that it has at least one bound state? Okay, that would require the finite potential well problem. I can give you idea. I don't remember the wave functions for that, but yeah, what the problem they are saying is, till now what we are doing, till now we were doing this thing, right? This is infinite potential well, but in some cases it can be a finite potential V naught, right? So what the problem wants, that you have to uh, find for what value of V naught you have at least one bound state. There should be at least one. There can be more, but there should be at least one, because for some value of V naught, there is a possibility there might not even be one bound state. Okay, so you have to find that V naught for which there would be one bound state. But we don't have to solve it exactly because they want us to use the Heisenberg uncertainty principle, right? So if you can also solve this problem exactly, because if you solve this potential well problem, you can get the solutions like transcendental equation like this. tan x equal to x and cotangent x is equal to minus x, sort of these problems. Then you can plot these solutions, something like this, and put the line, and you can actually see what are the ground state. Okay, we are not going there, but I'm saying if you want to solve this problem exactly, you have to do this way. You have to solve the Schrodinger equation, you have to write the transcendental equation, and you, for whatever condition you want, what should be the potential barrier height for which you have the one ground state. Then you can figure that out from there. Now in the problem, what they're asking, let's try that. Let me take a screenshot. Okay. Let's put it there. So you have potential well of, where did it go? Yeah. So you have a potential well of width 3 nanometer. Let's say your A is 3 nanometer. So you have to find the minimum depth of the potential well such that it has one bound state. So for using the uncertainty principle, just think from where you can get the V naught. You can get it from delta P, right? So basically what you have to do, you take the uncertainty of the order of the width of the well, and you have delta P. And using the delta P, you can find the V naught, minimum depth, for which you have at least one bound state. So that would be your V naught would be delta P square by 2m, right? Which would be h bar square by 4, sorry, 8 ma square. Now what you have been given is these numbers. Okay, there is also E. Why do we need E? Oh yeah, to change the units. Fine. Right. So just put the numbers. You'll get this h bar square. See, in the problem, actually, we just need the order. Is it micro? Is it milli? Is it nothing? Or is it mega? So we can just take the orders. Let's say 9.3, h bar is 6.6. So 6 square, 36. 10 power minus 68 joule square second square. 8, 9 square 81. 10 power minus 31 kg, which is 62. A square, 3 nanometer. Sorry, there is also 4 pi square, which is 6636. Okay, yeah. So what else is there? A square, which is 3 into 10 power, which is 9 into 10 power minus 9 minus 18 meter square and kg. Okay. So you'll get energy in joules, right? Out of this. But you have to convert to EV. So you have to divide by 1.6. Divide or multiply. So 1 joule is 1 EV is 1.6 into 10 power minus 19 joules, right? Yeah, I guess so. Yeah. So 36 से 36 gaya, and you have 10 power 19 above, 10 power minus 68 plus 62 plus 18 by these terms, 8 into 81 into 9. So which is of the order of what? 8 8 is 64, 64 9s are 10 power 3. So yeah, this would be amounting to 10 power 3. So let's see what the number is. 19 minus 6 plus 18 minus 3. 13 minus 10 minus 10 plus 8. Oh my god, this is a big number. How is it possible? A is nanometer square. Fine. Oh, fine. Okay, I got it. So mass was not squared. We squared the mass. It has to be 9 into 10 power minus 31. Eighty-one eights are 64. So it's a 10 power 2. So 19 minus 68 plus 49 minus 2. What is that number? 49 plus 19 is 68 minus, this is 10 power minus 2. Are you kidding me? Okay. 68 minus 68, and there would be also, so it's milli EV, right? It should be milli EV then. 10 power minus 3, because there is also 1 by 6. So it is milli EV. Hopefully, yeah. With this factor also. So is that the correct option? Hello?
Yes, sir. Yes.
Okay, fine. So this is how you can estimate the orders. You don't have to make full calculation. Okay, what else? Any other doubt? Any other problem? You can put it in the chat box. Because I'm here for another half an hour. So you can just ask, you can talk about quantum mechanics.
Yes, the highest possible electronic energy for the any hydrogen atom will be infinite, or it will be same like ground state energy, 13.6 ev.
No. So minus 13.6 is the lowest, right?
Yes, sir.
So the spectrum is like this. Okay. Uh, it's like, it won't be greater than 0 definitely. So yeah. So okay. Well, how do you write the energy of the hydrogen atom? It's minus 13.6 by n square, right? So for n equal to, wait, I need to put this on chart, otherwise it would get disconnected. Just a second. Yeah. So for the hydrogen atom, this is the energy eigen value, right? So for n equal to 1, this is the minus 13.6, the lowest.
Yes.
So the spectrum is something like this. It would keep reducing and it will go till all the bound states approach 0 eV. So it's a continuum here. You call it continuum. These are the discrete sort of. Right? So the highest would be 0 when n tends to infinity.
Yes, I have sent in chat box. It will be till infinity, right, sir?
Yeah, right,
Right.
right. Uh, The highest possible as an energy. What is it saying? What answer is does it say?
Say infinity.
How is it possible? It won't be eigenstate. Highest possible energy can be infinity, but it won't be eigenstate. It should be zero. Mm, for n tending to infinity, it should be zero. Maybe it might be wrong. I mean, it's zero. As you can see, it's if n is minus 13.6 by n square, then for n tending to infinity, which is the highest possible state, your minus 13.6 by infinity square would be zero. So it can't be infinity. The energy can't be infinity. The number you can say infinity. Yeah. Maybe I can discuss in the next class. Maybe I'll look into it, but according to me, it would be zero only. Yeah. What else? Does anyone have anything? Or we can do one or two more questions, then just solve it. Yeah.
Sir, one question is
Yeah, yeah.
in chat box.
In chat box.
Sir, but why they are showing infinity to that answer?
I don't know. Maybe I'll look into it, and next time, next Sunday, I can discuss with you. Yeah.
Okay, okay, sir.
Yeah. Because I don't. It doesn't seem infinity. Yeah.
Mhm.
Yeah. Okay. We can do something interesting. This is simple. This is also simple. This is simple. Huh, we can do this thing. So till now you have just discussed the one dimensional box, right? When you have just one variable. If you have a box potential in two dimensions, let's say it's like this, it's like sort of this. So you have a x, you have a y. So between 0 to a and 0 to a in y, it is 0, the potential, but here it is also going to infinity, here infinity, infinity, infinity. So it's a two-dimensional box where between x, y, 0 to a, you have vx0, otherwise vx infinity. Right. So if you solve this Schrodinger equation, how do you solve this Schrodinger equation? Like it's very simple to solve, right? In what case? One dimensional box. So does anyone have idea how do you find the eigenvalues and eigenfunctions for this? Does anyone know for this potential how you do that? Hmm? Anuj,
And so,
do you know how do you do it for one dimension? So okay, let's do this. So right, x square by 2m d square psi by d x square, where is a function of xy, and you also have the term d squared psi xy by dy square plus vx y psi of xy, and you have this is your eigenvalue equation now. So you solve this by method of separation of variables. what you can do, you can take your function of x and y as some psi of x and psi of y. Then you reduce this equation to two different equations in x and y, right? Then you get the Schrodinger equation, which are similar to the 1D box for both x and both y. So from that, you don't have to solve the equation again. You can just say your wave function would be root 2a times sine n pi x by a and root 2a times sine n1 n2 pi y by a. And your energy n1 n2 would be n1 square plus n2 square by h bar square pi square by 2m a square. Right? If you do that separation of variable, you'll get two Schrodinger equations which are similar to 1D box in x and y. So from that, by simple argument, you can write your combined wave function in x and y, and you can also write your energy En1, N2. Fine. Okay, just a second. Yeah. Huh. So now what does the question say? You consider a particle in a two-dimensional box whose ground state energy is epsilon naught. Then the energy E, which is 13 epsilon naught, would be non-degenerate. We have to claim whether it's true or false. We have the energy, right? This is the energy. The ground state energy is what? When it is this thing is 1. Either it can be N1 0 or N2 1 or N1 1 or N2 0. So it's a two-fold degenerate ground state. Right? What is the ground state? Epsilon naught is h bar squared pi square by 2m a square. So your any state n1 n2 would be n1 square plus n2 square times epsilon naught. Now in question you are given it is 13. If this is 13 epsilon naught, is that non-degenerate or not? Can you think of any two numbers, any two integers, whole numbers, which can be the squares of that sum should give the 13? I mean,
Two.
you can 2 and 3, right? There is a guest. Okay, so yeah, 2 and 3, that is 13. So now n1 can also be 2, n2 can be 3, or n1 can be 3, or n2 is 2. So again, this state is two-fold degenerate. There are two possible combinations of N1 and N2 for which you can get the same energy 13 epsilon naught. So that means the state 13 epsilon naught is two-fold degenerate. It's not degenerate. I mean what I'm saying, it's degenerate. Yeah. So the statement is false. It's two-fold degenerate. So now there is a similar problem to this in the cubical box. Cubical box, that means you can think in sort of four dimensions. How? Because x and y and z are the variables where this box is defined, and the another fourth coordinate is the strength of the potential. I can't draw that potential. It was easy to draw this two-dimensional potential because it's also 3D sort of, because potential is in the z coordinate. But in that case, it would you have to imagine it like it's a box in a whole space x, y, z, and inside the box your potential is 0, but outside it is infinity. So you shade the outside region as infinity, but inside as just keep it 0. So in that case, what will your be eigenvalues? It would be, how do you write, n1 n2 n3 n1 square, n2 square, n3 square, h bar square pi square by 2ma square. This is nothing but the ground one, Eg. So your condition would be, okay, so they're asking for the sixth energy level, what would be the degenerate state? What would be the degeneracy? Okay, you can put all the integers, all the possible integers, and you can get this spectrum en1, n2, n3. And usme if you do, you would see that your sixth state would come out to be 14 Eg. ठीक है, तो 14 Eg है, तो your n1 square plus n2 square plus n3 square would be 14. Now how can it be 14? It can be with 1, 2 and 3. And if you have three different digits, 1, 2 and 3, and you want how many possible cases it would be? It would be 3C2, which is 6. So there would be 6 degenerate states for the sixth energy level. So it would be, yeah, let me see, is it correct? Yeah, it should be correct. Yeah, I think it's correct. Yeah, 3C2. So your immediate sixth energy level would be 6-fold degenerate. So this is how you can find the degeneracy of a state, of an energy level. Yeah, right. What else? We can do this last problem. This would be a different one. So it's about conservation of momentum. It's not exactly quantum mechanics, but you get to
Sir,
see sort of. हाँ बोलो.
uh, do sir, there's a Runge lens vector that has done. Can you ask question from it?
Runge lens vector. I have studied that, but I don't remember it fully. So what's the
Okay,
question? You can tell me the question. I can come up with the thing in the next session.
okay, sir. I am.
Post it on the chat box.
Okay.
I'll take the screenshot. Okay, you have sent some questions also.
Yes, sir.
Oh, this is Runge lens vector. Oh, okay, fine. I think it would not require exactly for you to know Runge lens vector, but yeah, you can do such
So
things.
actually, I am preparing for gate now, so some question maybe from like that.
Right. Okay, I understand. Let me take other screenshots also so that I can solve these questions.
So,
Yeah.
so when you click on the photo, that will download also. No need to take capture.
Oh,
Yes, sir. If you will click on photo, it will download.
I can just down. Oh, yes. Fine. Right. Okay, I'll download it from the chat box later onwards.
Okay.
Fine. So what's the question? You have an operator ji, jx, and jy. You have to find the expectation value of this. Acha. Expectation value of what? Oh, the question was not properly. Right. J equal minus m equal half. What does that mean? Acha. Right. So, right. I understand what is it. Yeah. So how to solve this? I can come up with the full answer for this question next time, but I can give you idea how to do that. So it's very simple. So you have an operator ijx jy. They want you have to find the expectation value for the state j equal minus m equal half. That means j half m minus half. Right. So you have to basically find half minus half expectation this thing in bracket notation. What you have to use is, you have to just use, when you operate jx and jy on this half minus half, what do you get? So these are nothing but these. Then what you have to do, you have to do this in terms of ladder operators. You know your ladder operator, this is this, and this is plus ijy, right? So you can write jx and jy in terms of j plus and j minus. Okay, so after that, you know j and m are the eigenstates of the either j square and the jz. So what you have to do, then you have to yeah, so from that you can use this relation, j plus jm is h square square root of j plus 1 minus m plus 1 jm plus 1, and for j minus you can use jm as h bar square j plus 1 minus m minus 1 j m minus 1. So you have to write, so the idea of doing this question would be, you have to write jx and jy in terms of j plus and j minus, then you have to operate j plus and j minus on half and minus half state. Then you will get the linear combination half minus half out of this also. So you have to see what is the contribution from that part after you apply this operator. So that would something turn out to be something like what you have mentioned in the problem, the q h bar square by 8. So then you can actually figure out what the q is. So
Okay,
you
sir.
understand how to do this
Yes.
problem, right?
Yes, sir. Here we have taken first J plus and J negative. That's the value. How we get that? Can you please? Yes.
This thing, how
Yes,
do
sir.
you get this thing?
J plus J
So
minus. Sir.
you can get this thing very simply. So you just need to know this thing. And you had to know this thing. Then by knowing that this thing, that jx square plus jy square plus jz square is equal to j square, you can get the condition for how the jx apply on jm, sorry, j plus. If you convert it into the j plus and j minus, then you can get this thing out for j plus and j minus.
Yeah. Okay, sir. Sir, how we know that we have to convert in J plus and J negative only? This is the only procedure to solve
Because
this.
no, because you don't know how jx operates on jm. If you know, then fine. But what my strategy is always is to go to ladder operators. Even with the harmonic oscillators, you don't remain to the ax and ay, because there are a dagger and a, right. Know the operator. There is annihilation operator and there is a creation operator. So you always try to go to this annihilation and creation operators thing to exactly see how it operates on the state. In every problem, you should always do this thing.
Okay. Okay, sir. Thank you.
Yeah. Right. So these are good questions, but these were not relevant to what we have today, but that's fine. Okay, I'll go with the other two questions, because that this looks like the classical mechanic question, right? Not quantum mechanics. But yeah, I can help you out with that. Yeah. Anything else?
So there is one question also in chat box about, yeah.
Which one? This?
Yes, so there is,
Yeah,
and let,
this is classical. So actually, I know the answer. It's so for what values of n are the circular orbits stable if the potential energy is this? This is a classical mechanics question, right?
okay, so
Not
then,
quantum mechanics. What do you think? What would be the answer? You can actually solve this, the condition. It's a uh, it's I don't remember what value is this, but you can solve this.
Okay, sir. Then leave it. Another question is also in checkbox for quantum.
Okay. Hmm. So you have Runge lens vector. Okay, is given by this. K, fine. You have L and 1 by R. So we have to find what? It's the commutation relation or Poisson bracket. Is it again a quantum mechanics question or classical? Let me read. V is minus K by R. Fine. R is x square plus y square. And L Z component is this. Fine. And the Runge-Lenz vector is this. Why do we need Runge-Lenz vector? You can just do this operator, right? L and 1 by R.
Okay.
What do they want? This is commutation relation, right? Or is it Poisson bracket?
Sir,
Because it looks like to me it's classical mechanics question. You should know how to calculate the Poisson bracket.
but sir, in it's given na that's a Runge lens vector. It is comes in quantum only, na, sir.
Uh, as far as I have seen, it is in classical mechanics. I have used Runge-Lenz vector,
Oh,
but
okay. Sir.
right.
Maybe I don't know.
Yeah, maybe I'll solve this and come up with the solution in the next class. Yeah. Anything relevant to quantum mechanics? The one till the week 2, whatever you have been taught.
So there is a basic question related to quantum. Sir, why we create any barrier in the depth in the well? Uh, in
Okay, so
yes,
okay. So why do we have barrier? Okay, but that's the answer is in the hydrogen atom problem. Hydrogen atom problem is itself a barrier problem, right?
sir. Uh, how, sir?
Because see the barrier. How does barrier come? If you have a system, there is nothing, there is no barrier. But if you put an atom, suddenly you'll get a barrier, no?
Okay.
Because there are electrons around the atom, right? So if you are, let's say, the in a condensed matter physics sort of idea, what you have, if you have a material, there are atoms, and if you consider a gellium sort of model, then what you have positive ions and you have electrons, right? So sort of electrons are feeling this barrier and because of these atoms, right? So that's where we need sort of these the uh,
Barrier.
barrier sort of problems, yeah. So it's whenever there is some disturbance in the system, that is the
Okay,
barrier.
that's why we create the quantum well in that any uh, uh,
Yeah.
square quantum well.
That's where you that's the well actually well sorry, yeah. So atom is well problem, right? Yeah. So what you're asking, there is barrier. Where is the barrier problem, right? That's in the way it's tunnel, I guess. In the helium atom problem, the tunneling, you would need this barrier problem to get the tunneling current for the alpha particle, like how how much the probability that it will tunnel through. So something would tunnel through this. That would be the barrier problem.
Okay.
Yeah. Okay, so I think we'll end the today session. Yeah. Yeah.
Yes. Thank you, sir.
Okay. Bye. See you next
Thank
Sunday.
you,
Thank you, sir. Thank
sir.
you.
Okay.
Please share the video, sir.
Yeah.
Please, can you share the video, that recorded video?
Yeah. So it would be shared in the. Okay. Yeah. So I'll stop recording. It would ultimately go to the chat box.
Thank you, sir.
Yeah. Stop recording. Are you sure? Yes.